Hi, today I'm going to talk about the value function approximation. So first of all, before this video, we discussed about implementing reinforcement learning and the most naive approach, which was using a V table, which is a value table, or a Q table, which is a action value table. So what we were doing was basically representing the action values or values with a tabular representation in a matrix form. So this might be the most intuitive way, but when the state space gets larger, because each data cell in such matrix is, for the value function, is a state, for an action value function is a state action pair. So as those state space or state action space increases, which is a very common case in the real world problems, it becomes infeasible to implement it. So there must be an alternative to deal with that scaling problem, which is here introduced as the value function approximation or action value function approximation. So what kind of advantage can this give? First of all, as I just said, it could save a whole bunch of memory, which is in terms of the matrix. We don't have to store every state action value or state value. So that's the first advantage. And the second advantage that we can also generalize. If we don't store all the values for, say, state action pair, but instead make an equation, if when it comes to a linear, it could be a linear combination, anyway, the gist of the function approximation is that we use parameters. So the input for the value or action value would be the state or action. And then based on the parameter weights, it outputs a value or an action value. So the keyword is parameter. And the number of parameters, so the parameter is what basically determines the time learning complexity of the algorithm itself. So the number of parameter is always smaller than the state action pair, or a number of states or number of state actions. That's why the reason for using functional approximation, to decrease the complexity. So if we have a set of parameters, that means that we don't have to figure out the values for all states or state action pairs, but just can, even for unseen state action pairs, we can just output a value using those parameters in the equation, which is basically, in a formal way, we are generalizing from seen states to unknown unseen states. So this parameter, the weights, should be trained, and the method for training those weights is discussed in the prior videos, which is using either the Monte Carlo method or the temporal difference learning method. So this is the basic structure for which describes this value function approximation. As I emphasized, we could either output a value. It could either be a value function approximation or an action value function approximation. Action value is Q, right? And for approximating this action value function, there can be two forms. One could be just inputting a state and outputting an Q values for a state and associate all of the associated actions, action 1 to action M. And the other form could be just both inputting the state and action pair itself and just outputting a single Q value for that particular state action pair. So since we are approximating the function, the approximator could be in many forms, which it could be just a linear combination of features, neural network, decision tree, and so on. But the important point in terms of updating the weights is that the function approximator should be in a differentiable form. The objective function should be differentiable because we want to do the partial derivative of the objective function with respect to the weight, the parameter, so that we could figure out the gradient, which is the factor that is used in the updating the weights in terms of calculating the new weights from the old weights. And also, since this context is basically in reinforcement learning, which unlike supervised learning, we're not dealing with stationary or IID data assumptions. So the training method used in this function approximation should also deal with that untraditional, not traditional data, which is non-stationary and non-IID. So in terms of value function approximation, there are two, you could categorize it into two methods, which first, we will first go over the incremental method, which is basically a more online, it's not exactly analogous to online, but anyway, the idea is that we gather the experience and then perform the gradient descent. Like, I mean, we update the weights and then discard those experience and repeat that process so on until we converge or sometimes unfortunately diverge. So the concept of gradient descent is basically, let's say that we have here a JW, which is in this context is going to be the objective function in specific, which, yeah, okay, so objective function, which is, which contains the parameter vector. So the objective function is the differentiable function of the parameter vector weight, W, weights. And the gradient of this, so this parameters is likely to be multiple. It could be one, have a number of one, but parameter could be one parameter, but it's typically a set of parameters. So the gradient of this objective function would be a vector of the partial derivative of the objective function with respect to each weight. So weight 1 is for parameter 1, weight 2 is for parameter 2, and so on. So this is the gradient of the objective function, which will later be used for the update of the weight itself. And our goal is to find the local minimum of this object in the surface of the objective function. So as you can see here, the modification of the weight formula is given here, which is this constant term is basically used to make the equation neat later when this gets expanded, when this formula equation gets expanded. And this alpha is the step size parameter, which is basically the learning rate, because we don't want to drastically, like if we're trying to, in this contour, if we're trying to get to this, let's say that's the middle of here, the small circle is the local minima. In fact, here is the global minimum, let's say. We want to go there from this point. So, but the thing is that at some point, if we advanced too drastically, then we could just pass this minimum, global minimum, instead of converging to it. So to avoid those kind of situations, we want to control how much we advance in terms of the red line, how much we advance in terms of this red line. So this alpha is controls how much we want to advance in that graph. And then also, as I emphasized before, the other factor that contributes to the update of the weight is the gradient of the objective function itself. So what's the exact objective function in this case? Typically, we use the mean squared error as the objective function. So our goal is to minimize the mean squared error. And so here, what's the error? Here, the error is, since it's a value function approximation sub issue, the fitted, we are trying to fit the value function with our parameters. So this is our estimation of the value function, and there should be a true value function as well. And let's assume that we know the true value function. In fact, in reinforcement learning, we are not dealing with already labeled data from the beginning. We are trying to estimate the labels in progress of learning, in progress of when the agent is interacting with the environment. So we don't have such oracle which tells what's the true value function from the beginning. But let's just assume that we know that. And so in the assumption that we know it, we calculate the mean squared error. And then that makes the objective function which we want to figure out the weights that minimize the mean squared error. So to figure out the parameter vector for such minimization, we would have to update the weights until we converge. And the previous equation that I introduced, which is here, can be expanded into this alpha times the, okay. So as you can see, the gradient of the objective function can be expressed, which is JW, can be expressed as the multiplication. Okay, so naively, it's the alpha times the full gradient update. You can see the expected value towards based on the policy. So it's the error term multiplied by the gradient to the fitted value function. So in terms of higher level idea, when we're trying to update the weights, we are moving a little bit toward the direction where the direction of the error term based on a little bit of factor which contributed to that error term, which is connoted in the gradient of the fitted value function. So that's the intuition. And here we are dealing with the full gradient update in this equation, which means that we would have to use all the data because it's expected, all the data to calculate the gradient update, which is very inefficient computationally. If we have a huge size data, then it will take a very long time, which we should avoid. So that's the reason that we have to do the stochastic gradient descent, which is instead of averaging out, getting the expected update, we just sample we just sample the gradient and then calculate the weights and update the weights, and we repeat that process for one sample iteratively. So we can, and this empirically also converges to the local minimum. So we don't want to deal with the full batch gradient descent. We can be happy with even though we only do the stochastic gradient descent which basically sample one data and then perform gradient descent on that, do sample the next data and do it again, so on. So that's the idea. So in terms of value function approximation, so I've mentioned that we want the function approximating matrix function, we want it to be differentiable, which could be either a neural network or a linear combination of features. So let's first dive into the linear function approximation, okay? So when it comes to the linear function approximation, basically instead of dealing with all the states or state action pairs, we just want to use a smaller number of features. And that feature space could be represented as a feature vector. And so the feature could be anything, like which is informative in terms of representing the state. It's not the state action itself, but some factor that can explain the state space pretty well. For example, as an example, it could be if we want to approach a goal from this location to that location, if it was a state space, if we were using the tabular state space form, it would be state 1, state 2, state 3, and so on, right? But that could be also expressed as the distance from the goal location instead of just using all memory for each space. We don't want that. It's too expensive, right? In terms of memory. So we could just use a feature which keeps tracks of the distance between the agent and the goal location. So that could be a feature, or there could be other kinds of features in that environment. So that's so now we're just using one feature instead of dealing with a bunch of states, right? So that's where the computation gets scalable. So that's the idea of the definition of the feature, and we could have multiple features like that, which makes a feature vector. Okay. So when it comes to feature vector, the value function it's basically like we're trying to express in terms of a linear form, linear combination of features. So it's basically a dot product between the feature vector and the weight vector. And in this case, since that dot product is basically the function of linear function of value function approximation, that's the fitted value function, which you want to figure out the error term with the error against the true value function, which we assume the oracle tells us, and then that becomes the key factor for the objective function, which is basically the mean square error in this case, the JW. And then based on that objective function, we apply the stochastic gradient descent, which we went just before, to figure out the global optimum. And in this case, for the linear function, the mean squared error displays a bowl-looking surface, which means that because in a bowl, if you advance to the center of the bowl, which is at the most lowest point, anywhere you start, you likely converge to the lowest point, which if the surface looks like a bowl, right? So that's the reason why with linear value function approximation, the stochastic gradient descent converges to the global optimum instead of some local optimum. It's converged to the global optimum. That's the point. And in this case, the update rule, the general structure of the update rule is the same as what we discussed before, which is the learning rate multiplied by the error term multiplied by the gradient of the fitted value function. But since the value function itself is the dot product of the feature vector and the weight vector, the gradient of that fitted value function, which is basically the partial derivative with respect to the weight, is the feature itself, right? So formally, that's how the update to weight formula looks like. But intuitively, the gradient of the fitted value function is the feature. Intuitively is because let's say that we observe some error. So what would have most credit to that? What would be the most what factor would have the most responsibility for that error? We are to correct that error, right? So we have to figure out what kind of factor is most responsible to it. And obviously, the feature vector for a specific state, let's say that the feature vectors, there's feature 1, feature 2, feature 3, and so on. Some features can be off, right? At some time step, some feature will be very irrelevant, while some other features are deterministic, have relevance. So for the error at time t, the features that are on instead of off, which are relevant to that time on that time step t, should have most responsibility for the error, right? And in terms of the update to the weights, the parameter, those features that are responsible should have most account in terms of the update. So that's the intuition behind why the gradient for the fitted value function for the linear value approximation is the feature vector itself. And also one thing to note is that, like before, I have mentioned that the tabular form, which is the most naive way, and it could give an impression that the table lookup, which is formally called table lookup feature, is something independent from the linear function approximation. But in fact, the table lookup approach is a special form of this linear function approximation approach itself. Because as you can see here, the feature vector for the tabular representation could be just an indicator, a vector of indicator functions for states. And in this case, the value function could be expressed as the value function of the indicator function, vector of indicator functions for each state times the weight vector, which weight is basically in the tabular representation, the data cell value. So it's just another way to represent the tabular representation. Okay. So previously, I said that we are assuming that an oracle is telling us what the true value function is, which is very untrue in a reinforcement learning setting. So how would we try to figure out the true value function? It's the same as the previous in the previous videos, right? We could either use the Monte Carlo method to figure out the noisy but unbiased estimate for the return, which is basically we just let the agent interact with the environment until it hits the terminal point, and then that will get the target, right? That's the Monte Carlo method. And or the other opposite, which is TD0, temporal difference learning of one step, which is just interact once, and from the time step onwards, we just use an estimation, which is much less noisy, but more biased return. And in between, there was a thing called the TD lambda, which is basically get just somewhere between the Monte Carlo and the TD0, which is trying to get the use the trade-off, utilize the advantage and disadvantage for the both approaches. So all three methods are valid approaches in terms of estimating the estimate and get the true value function, as you can see here. So the Monte Carlo, when we're trying to get the estimate the true value function with Monte Carlo, first of all, it is valid. It's a very noisy but unbiased data. So one thing I want to emphasize is that it will converge because it's still a real data, despite it's very noisy. There's no such bias here because we're actually, the agent is actually interacting with the environment until it hits enters some terminal point of the environment. So it will converge to an optimum. And given this nature of robust convergence, it will converge even when the value function approximation is done by nonlinear functions, which nonlinear functions have much more divergence issue compared to the linear functions, obviously. So that's what to take from the Monte Carlo with value function approximation. And when doing the TD learning with value function approximation, as we know, we can still apply. We can make a bunch of training data by interacting once or n times, and afterwards we can estimate. We can still do that. And the thing is that the linear, when we do TD learning with linear value function approximation, it does still converge close to the global optimum. But with nonlinear function approximations, value function approximations, then it's very difficult to say that it will converge. And TD lambda is basically, as we can see, we can do it with both cases, which is, we know that TD lambda has subcategories of the forward view and the backward view. And when we do with the linear temporal difference learning, when we do with the linear combination of value function approximation, then we're just simply substituting the return to the true value where the true value function was. And when we do with the backward view, linear TD lambda, then we know that the backward view is basically using eligibility traces, which is composed of which exploits two heuristics of the recency heuristic and the frequency heuristic. So the recency heuristic, and so basically the eligibility trace is based on two terms, which is one discounting by the discounting parameter and also the lambda parameter. And also previously, the second term was the indicator function, but now it's the feature value, which basically comes from the gradient of the fitted value function. So the reasoning for this feature value appearing here instead of the indicator function is basically the same as what I said. It's basically giving credit to features that were on at some time step. So it's just differentiating across features that are responsible for the TD error at the point of time and the features that are off, which are not less responsible to that TD error. Okay. And note that the forward view and backward view linear temporal difference lambda are equivalent, which are proven, but which do not seem to be intuitive in the beginning. So if you want to do if we instead of just predicting, which is policy evaluation, if you want to do the control, if you want to do incrementally control the algorithm, which is basically associated with policy improvement, in terms of two-step process, we know that control when it comes to control is comprised of two steps: the policy evaluation and the policy improvement. So the value function approximation factors in the policy evaluation step, which we are approximating the Q value or the value function, Q action value function, or just the state value function. We are approximating that with another function approximator instead of using the tabular form, which keep tracks of everything. We don't do that, right? And then after approximating that with that approximated Q value or state value, we improve by the epsilon greedy policy approach until we try to hit some kind of the optimal Q state, Q values function. Okay. And I think I said it a little bit early, but we previously were explaining, I previously explained based on the state value function, but it could be done in the same way using the action value approximation, using the action value function, which, as you can see, the linear combination, linear action value function approximation is possible, which is similar to the value function approximation. And also here we still don't have oracle, so we have to estimate the true action value function either with Monte Carlo method or temporal difference, one-step temporal difference, which is TD0 or TD lambda. Okay. So this is a specific example, which is a mountain car problem, which we are trying to hit the goal in this V-shaped valley by a continuous state space, but with a discrete action space, which the action is composed of stop or accelerate. So it's basically a bang. In control theory, it's a bang optimal control problem. So, okay. So in this case, the main idea from this here is that we are using, in terms of value function approximation, we are using the linear combination function. And with the on policy temporal difference learning, which is SARSA, right? So SARSA is on policy, which the policy that we follow and the policy that we want to learn are basically the same. Okay. So when we are using this value function approximation for temporal difference learning in on policy setting, then as we can see, the value function converges to its true value function. And it's, as you can see here, the surface of the true value function becomes like a spiral, like it looks like a mountain, a spiral in a spiral. It looks like a spiral here, right? The spiral mountain. And here we can note that also for the features here, which we have mentioned that instead of keeping track of all states for data cells for all states, we are trying to use some features when it comes to the linear combination of features, right? So the features used here are the positions and velocity, which are two. And so based on these two features, we converge to this surface, which looks like a spinning mountain, which is the true value function. But note that other features. This is still the true value function, but note that we could add other features that might help learning the value function, true value function. And in that case, the instead of looking like this spinning mountain, the value function surface would look like a different form, but it doesn't matter in case like if we could minimize the mean squared error. Unless if that's satisfied, then it's all good. So also, should we bootstrap? So what do we mean by bootstrapping? Bootstrapping is basically estimating some function based on the estimation based on another estimation. So when it comes to reinforcement learning, TD learning setting, we are estimating the value function or the action value function for time step t based on the estimation for the value or active value for from on time step t plus 1, right? So that's basically basically bootstrapping is. So we know that the Monte Carlo does not bootstrap at all because we are not using any estimation. It's just rolling out the agent until it hits the termination point. There's a real interaction. So, and the lambda of TD lambda, that lambda hyperparameter is basically what controls between the algorithm becoming Monte Carlo or the naive TD, TD0. And as you can see here, across different environments, which is different problems, the lambda that turns out to be optimum in terms of the error varies by different games, different environments. But typically we can see that when it becomes completely, when the lambda is 1, when there's no bootstrapping at all, the error is very high. So it means that empirically we do need some bootstrapping feature in terms of estimating the target. But we can also see that in a lot of, at least in this 4 examples, when we are just doing the naive TD, which is one step TD, TD0, it's not optimal as well. So that means that it is worthy to try to figure out the optimal lambda per an environment, a specific environment. And also remember that the convergence with linear SARSA here is because SARSA is a TD learning on policy. And I also, so to categorize TD learning paired with on policy does have exhibits convergence behavior in many settings. And Monte Carlo method, it always converges because there's no such bootstrapping, no estimating feature there. It's just pure noisy but true value function, right? So there it converges anyway to some, at least to some local optimum. But when the TD pairs up with off policy learning, which off policy is the policy that the agent is following and the policy that the agent is trying to learn are different. So an example, so it's basically trying to learn like, okay, so a more intuitive example for on policy and off policy learning is basically, okay, so off policy learning is me. I am trying to learn about swimming based on looking at another person trying to swimming, right? It doesn't only have to be another person, it could be another animal. So based on another agent's experience, I'm trying to learn some kind of activity about it. But that's for the off policy. So it's learning, looking across another agent, looking to another agent. But the on policy in that analogy, in that example, would be go into the swimming pool and swim and learn about swimming while so which is what really happens in usually to a lot of people. So that's so what I'm trying to learn and what I follow is the same. That's the on policy, right? Okay. So when this value function of TV learning with which is value with along with the linear value function approximation associated with the off policy learning does have counter examples for convergence, which means that in other words it likely diverges instead of converging. And one of it is Barr's counterexample. So in this figure, if it was on policy, which is basically SARSA, let's assume we're using TD learning. The agent selects one action, right? And then goes to state 2, learns that policy, and then based on that same policy, it chooses the next action and so on. It learns like that. It's like rolling into an environment. But in this case, the values here are updated like swifting in all states instead of on policy. It's just updating this first state value function, the next state, third state. It's not something sequential. It's like sweeping the states in the same, say, a same line, right? So in this case, the parameters along with the value function approximation, which involves parameter, the parameter diverges instead of converging, as you can see here, as iteration advances. Okay. So the key point is that value function approximation, linear at least, along with off policy, does not converge, and of course, not even nonlinear. Nonlinear is much more unstable than linear. Okay. And of course, there's a thing called the gradient TD learning, which follows because the TD learning that we just discussed doesn't follow the gradient of any objective function, in fact, because there's so many estimations going on, right? Which leads to divergence issue. But the gradient temporal difference learning, which follows the true gradient of the projected Bellman error, does convergence in all cases. But note that this is only for the prediction problem, okay? The prediction problem instead of the control problem. Prediction in reinforcement learning is basically policy evaluation, and control in the reinforcement learning is policy evaluation and policy improvement chain. It's trying to figure out the best optimal policy by that two-step process. That's control. And this gradient temporal difference learning is mainly doing the prediction, policy evaluation, deals with the policy evaluation problem, which is prediction. And theoretically, it has superior performance to just the temporal difference, but in practice it's not necessarily better because theory and the practice is different. In practice, just using the TD learning could be sufficient. So there's not too much emphasis in using gradient TD anyway. Okay, so until now, we discussed about the incremental method of value function approximation, and another method which is not incremental. Okay, so to refresh, the incremental term comes from that we train the weights, we update the weights via the gradient descent by making experience, and then we train with it, we update the weights with it, and discard that experience and get the next experience, and so on. So there's some incremental property there, right? But the disadvantage of that incremental approach is that it is not data efficient. It's not sample efficient because we're just discarding an experience, which is a sample training data here, right after we we update the weights via the gradient descent. So a more data efficient approach would be to make use, instead of just discarding the data right away, you would like to save it into a batch, which is the reason why this is called the batch method. We want to save it and extract the most juice out of that data instead of just discarding it right away. Okay, so that's the intuition. So formally, it could be said as this batch method is trying to find the best fitting value function using all the data that we have seen so far, instead of just using it and forgetting about it, using it, forgetting it. We don't want that anymore, okay? So in terms of this batch method, it's basically very similar to the supervised learning, because we are saving a data set. So in the incremental method, we could more think of like a queue, queue data structure. It's just, we use it, we pop it, we push it, pop it, like that. So it's like kind of a memory, small memory of the medium which is very frequent and going in and out. But now we're using a batch, which is more like a supervised learning setting data frame, which we are using in the whole with the batch itself. That's a resource for training the data now. We don't have that going in and out feature anymore. So with this batch approach, we could use the least square prediction, which we know least squared, right? So still, we are trying to do the value function approximation, right? But now we make a data frame which stores the experiences of a tuple of state and the associated value. State 1, estimated true. And the thing to note here is that, okay, now we have a batch, which is in fact a data frame. Data frame might be consistent of data cells, right? And each data cell, think it as a tuple. The first element of the tuple is now the state information, state 1, state 2, so on. Okay, and then the second element of the tuple is the true value function, which is gained by actual experience. Because the true value function is basically, it's not an estimate, there's no estimated property there. We can only get it by the agent really interacting with the environment. So we accumulate those experiences and make it into data frame. That's batch. So using that batch, a huge data frame, you want to learn the parameter. Like what's the best weights, the parameter vector, what's the value of those weights in the parameter vector that gets the best fitting value function, which that's our main interest, right? And also, if we figure out the value function, fitted value of the function approximator, then we could again do the gradient descent thing, right? Which here is basically the least square. So here note that instead of using we could either use some of squared error or the mean square error. It doesn't matter. And also, when we're trying to now we have a huge, let's say that we have a huge batch, but should we, in this case, just update the weights based on the whole data? What if the data is too big? This is again the problem that we faced before. The trade-off between the stochastic gradient descent with the full batch gradient descent, full gradient descent, which either using the whole data to get the expected update, or just performing update based, just sampling one sample and performing update, then sample one more, perform update, and so on. So there's a trade-off there, right? Which we preferred the second one, which is sampling, updating, which is called stochastic gradient descent. Even in this case, we prefer that. So what we're trying to do is we will use a concept of experience replay, which is basically the batch, what we said before, the data frame. And so we sample one data from that experience replay. And here, since now, and also this experience replay has a great advantage that we are breaking the correlation of the data, because the reinforcement learning data is non-stationary and non-IID, given that we are accumulating data based on sequential interaction with the environment. So naturally, there should be a huge correlation between the data generated at time step t and time step t plus 1. So, and that is not good for any function a lot of function approximations, because, for example, neural networks don't like that because they assume IID assumptions, right? So somehow we want to break that correlation issue in the data itself. We want to make it to IID. And using this experience replay, we make a data frame out of the experience, and then we can just randomly sample one of it instead of in order. We could just unorderly sample it, which basically now it's becomes IID assumption, right? There's randomness there. So experience replay has such experience replay, which has such advantage, is now combined with the stochastic gradient descent. So we're randomly sampling one state value from experience data frame, and then applying stochastic gradient descent for the update of the weight, and so on until the weight changes becomes very small, or in other words, converges to some optimum. And this approach converges to the least square solution, which but note that it's done by a few iterations. So the iteration could be very long or very short. If short, great, but it could be very long, which could in some cases have some other alternatives. Okay, for those cases, there could, I mean, this experience replay combined this stochastic gradient descent has a huge advantage, but since it's done by a number of iterations, in some cases when the experience history is very complicated or crazy, the iterations needed to converge would be very long, which could be considered as a disadvantage, and some other methods could have some other approaches might have an advantage on this approach, which needed huge iteration, right? So yeah, so the experience replay, as I said, breaks the correlation, and it could be used with specifically an example. I did it explicitly in one of the videos that I discussed in the presentation about DQN, but here it is talking about it again. So to just shortly go over it, the DeepMind team came up with a single architecture, which is comprised of specifically the deep neural network, which is this convolutional neural network, CNN, which is basically usually for most well known for processing image classification, image data. And the DeepMind team, using the CNN architecture, was able to come up with a single hyperparameter set with a single CNN specific architecture to excel in playing like 50 games of Atari games, 50 Atari games. And the impact of this DQN in Atari was that it converges, because the main problem prior to this DQN in Atari was that using a neural network, the the weights didn't converge but diverge. There was a huge diversion issue because the neural network is basically a nonlinear function approximation, which is more prone to diverging, right? So, and the way the DeepMind overcame that diversion issue was by using an experience replay, which we went over, which is mainly decorrelating between the data, which is basically making the data more IID-like. And that's the first breakthrough. And the second breakthrough is that they use the fixed Q target, which is basically because if they're not using a separate target network, then it means that they are training both the estimated Q and the target Q using one single network, your CNN, which means that when the weights are updated, the estimated Q and the target Q both updates to the same direction, which in fact, the goal is to, the main idea for gradient descent is that we want the estimate Q, to more approach to the target Q. We want to, so basically what we're trying to do by doing that is reducing the error terms. So that's basically what we're trying to do, right? That's the objective function, the mean squared error. But if the target Q and the estimated Q moves toward the same direction at the same time, then it will not converge because the target Q is, the estimated Q is trying to catch up to the target Q while target Q is escaping from it. That's the main reason why it diverged. But they introduced a fixed Q target, which basically for the fixed Q target network, they freeze the weights for some C iterations. C is a hyperparameter, and then estimated Q try to converge, and then they copy and paste the learned estimated Q weights to the target Q, update after C iteration, and they do that process, which led to, which ultimately overcame that divergence issue, and now it is converges. So yes, so DQN was, yeah, so that DQN basically was a very groundbreaking, very great advance. That's the idea. And okay, so so that DQN shows that experience replay does find the least square solution, which is great, right? But as I said before, disadvantage could be a disadvantage when, because it's basically experience replay combined with the stochastic gradient descent is basically going through many iterations. So if that number of iterations increase in terms to converge, then it could be a disadvantage. So in some cases, instead of going through so many iterations using the SGD and experience replay, it's better to just use the linear least squares prediction, which is still a linear combination, which is not nonlinear as we did in DQN. DQN uses a nonlinear neural network, right? But the which means, okay, so it's very interesting to go over that. So the deep neural network is a nonlinear approximation function, and the advantage is that it's basically, deep neural networks is projecting from the original feature space, is projecting to another space, a feature space. So, which is more learnable to the machine. It's basically projecting from the original space to it's transforming the features space until it's transferred enough so the machine can learn well. Okay, that's the idea. And so there's some nonlinearity there, right? And the nonlinearity can be introduced by either, specifically, it could be an activation function, or when it comes to CNN, it could be like a pooling layer, or it just differs by different architectures. But the idea is that if we're trying to use the state-of-the-art deep neural network functionality with reinforcement learning, we cannot use it with the linear combination of features. Because mathematically, the linear combination of features, let's say that we want to use a deep neural network with 10 layers, right? So deep neural network with 10 layers. The first layer and the 10th layer, when it's nonlinear, the first layer cannot be expressed in a single equation in terms of the 10th layer because there's some nonlinearity there. But if it was only based on linear combination of features, then there's no reason to make the neural network deep because there's essentially no difference between the first layer representation and the 10th layer representation. They're just the same equation that's expanded. So that's why we can't use the linear combination of feature approach with deep neural network, which could be considered as a disadvantage for this linear combination of features approach. But when it comes to sometimes when it takes too much iteration, that I said before, given that the linear combination of features approach can solve the least squares solution directly in one pass instead of needing such iterations. So it's also a way to go for some cases, despite it's just linear, okay? So mathematically, the linear least square prediction, when the least square, which is here the sum squared, but based on some parameter vector with weights, we want to minimize the error, right? So when the weight change is equal to 0, which means that we're not updating the weights anymore, there's no need to update the weight anymore. That means that we hit the minimum, right, of the objective function, which is least square error, right? In this case, we can express that as the expected value for the weight change equal to 0, which now, since we can express the expected weight change, update in weight by learning rate times for each time step, like as we said, the update for weight formula, which is, okay, again, learning rate times the feature vector times the error. So now, since we have a formula, we can just collect the terms and then express it as a function of the weight, right? Which, as you can see, we do have to invert the matrix here in the closed form solution, which this inverted matrix, this part could be computationally expensive, relatively computationally expensive. So it's not just this approach is not just it's direct. We could just directly get the W, as you can see here, right? Which is advantage, it's direct, but it would require some computation. But so it's not just superior to the experiential replay with SGD approach. But when the experience replay with SGD gets too computationally expensive, which it means that the iteration is too long, then in some cases, directly computing this, despite this that inverted matrix computation issue, this could be faster. So that's when we would want to consider using this. Okay. And again, here, while calculating this function, we do need because we want to figure out in the closed form solution for the weight, it does include the true value function, which true value function is mainly coming from the error term, right? We have to know the true value function for the error to calculate the error with the fitted value function. And this, again, there's no supervisor in the reinforcement learning, so we would have to rely on the Monte Carlo method or the TD or the TD lambda to estimate that. again, and it all for all forms of LSMC, which least square Monte Carlo, LSTD, least square temporal difference, LSTD lambda, it all has its corresponding closed form solution for W, which is always direct. So always think about the trade-off with, so if you want to get the weights with batch method, always think about the trade-off, the complexity, time complexity, or spatial complexity these days not necessary, but time complexity between this linear least square approach and the stochastic gradient descent combined with experience replay. Okay. And also, this was basically a prediction problem again, what I just previously said, which was prediction problem basically policy evaluating. Okay, given a policy. To be very clear, the prediction problem is basically the prediction problem is a policy evaluation. We're just trying to figure out what the value of being in a state and following a policy would be. Okay, and we're iteratively doing that. Okay, but in the control case, we are trying to improve our policy after we estimate it, which is a two-step process: policy evaluation and policy improvement. And when it's combined, when that control is combined with the least squares, it becomes LSPI, which is least squares policy iteration. And in this case, the policy evaluation is done by least squares of Q learning. Okay, it doesn't have to be Q, it could be V, but anyway, most of the control problems are basically assuming model free. It's always model free in real world problems, because if it was model based, then we would have to know the state transition function, real function, which is unrealistic and computationally heavy. So we always want to go with the action value that we don't have to know about the model of the MDP. We just have to know the Q action value. Okay.